Everyone, today we're going to do a revision session on EECE 290 analog signal processing, especially the exercises on quiz 1, which are chapter 7, chapter 8 and chapter 12. This revision session is courtesy of the Culture Club of the South to help you study for the exams. So let's begin with problem 1. In problem 1 we have in the circuit above L is 0 Henry. The switch has been in position A for a long time and is moved to position B at time equals 0. So we have switching at time equals 0. The question is how much energy is delivered to the 5 ohm resistance in the time interval 0 to infinity. So we need the energy dissipated across the 5 ohm resistor for all time from 0 to infinity. So if you look at the circuit, we notice that we only have an inductor and some resistors. So we don't have a capacitor and inductor in the same network. So we know that we're not dealing with chapter 8, but we're dealing with chapter 7. So it's a first order response. Moreover, after switching, so if we have the switch going like this, we only have an inductor and some resistors in the network. So we know that it's a natural response. We don't have a source that gives energy to the inductor after switching. So after switching, the inductor will release all its energy to the resistive network. So we know that if I want to get the current in the inductor, it will be I of t. This is equal to I0 exponential minus t over tau, where tau is L over R equivalent, or R that is seen by the inductor. This I of 0, this is I at 0 plus, or this is equal to I at 0 minus, because the current across the inductor is continuous. The current can't do a jump or a discontinue during any time. It needs to be continuous across the inductor. So if we get the current across the inductor, we can also get the current across the resistor as well. The current across the resistor will be exactly equal to I of t if we draw it in this direction. And we know that the power across a resistor is Ri square, and the energy is the integral from 0 to some time of this Ri square dt. This question asks us the energy from 0 to infinity, so let t equal infinity, and we do the integration and we're done. So let us get the current in the inductor like this. So first of all, we need I0, which is the same as I0 minus. So we consider the circuit before switching. Before switching, we had the circuit like this, 40 ampere. We have a 4 ohm. We have a 20 ohm, a 5 ohm, and then a short circuit, because an inductor at DC level of voltage and current is a short circuit. More specifically because V equal LdI by dt, and if I is constant because we're at steady state, then this is 0, and voltage 0, this means that the inductor is a short circuit. So we need this current that's flowing in this direction, which is I. We can do a current divider, so if we do the R equivalent of these, this is gonna be 4 parallel with 20. So let's do the circuit again. This is 40 ampere. This is 4 parallel with 20, so it's gonna be 10 over 3. And then this is 5. And I need the current going like this. So by current divider, I know that this is going to be equal to 40 times the other resistor divided by 10 over 3 plus the resistor that I want. So if we do this calculation, this is going to be 40 times 10 divided by 3 plus 5. This is going to be equal to 16 ampere. So I at 0 minus, this is at time at t equals 0 minus. So at time equals 0 minus, the current was initially 16 ampere. And because this is the current across the inductor, it will carry over to time equals 0 plus, which is also by definition I of 0. So we know the first component of our solution. We know this. This is going to be 16. Okay? Now, this is step 1 of solving. Okay? Now, on to step 2. So after switching, we have the circuit looking like this. And we no longer here have switched, so this part of the circuit is disconnected. and we only have this part of the circuit, right? So what we can do is draw the circuit after switching. So we have here 16 ohms, here we have 20 ohms, right? Here we have 5, and here we have the inductor, but we really only care about R equivalent as seen by this inductor. So we need R equivalent in here. Why? Because we need tau. Tau is equal to L over R equivalent. And L is 0.4, we already have it given. So we need R equivalent as seen by this arrow. Okay, so easily we can do we can say that these resistors are in parallel, so 60 parallel with 20, and their combination is in series with 5. So whatever I get here, I add 5 to it, so plus 5. And if I do this, we get 20. So R equivalent, this is equal to 20, this is equal to R equivalent. So easily we get tau is equal to L over R, which is 0.4 over 20. So 0.4 over 20, this is equal to 1 over 50, so 0.02. So 1 over tau, this is equal to 50. This is in second, this is in hertz. So we have I of t, this is equal to the initial current is 16 exponential minus 50 t given in ampere. 50 t, the 50 comes from 1 over tau. So now that we have the current inside the inductor, we say that the current inside the inductor is the same as the current in the 5 ohm resistor. So what I can do is say that the energy from time equals 0 to infinity, we do the integral of the power. The power is Ri square with respect to time. So the R goes outside from 0 to infinity of 16 square exponential minus 100t dt. Because I do the square, I multiply this 50 by 2, and the 16 square is a constant. The energy is equal to 5 times 16 square, I carry it outside, multiplied by exponential minus 100t over minus 100, because the integral of e power minus ax dx, this is equal to e power minus ax divided by whatever is the coefficient of x, or the derivative in here, which is minus a. So this is our energy taken from time equals 0 to infinity. So if we evaluate the boundaries of this integral, we find 5 times 16 square over minus 100, and the exponential at minus infinity, this is 0, and the exponential at 0, this is 1, so minus 1. So minus and minus will cancel, and we have the energy is equal to 5 times 16 square over 100. This minus and this minus will cancel, so the energy total is 5 times 16 square over 100, which is exactly 12.8 joules. We found this energy, and here 12.18 joules, which is answer C. Okay, in problem 2, in problem 2, we have in the circuit above, Vs is 180, so this is equal to 180 volts. Okay, the two switches operate simultaneously. Switch 1 here have position was at position A and switches to B at time equals 0, same as switch 2. It's at C and switches to D at time equals 0. And we need to find V0 at 0 plus. V0, which is this, we need to find it at 0 plus. So we notice here that we have a capacitor and an inductor in the same circuit. But this is not after switching. If we have a capacitor and inductor after switching, then we're in chapter 8. But here, this is before switching. We have the capacitor and the inductor. So the inductor will act as a short circuit. It will not affect the circuit after switching. So we're still in chapter 7. And after switching, if we have the switches like this, this is the capacitor right here, and 40 ohm and 10 kilo. We don't have a source, so we know that the voltage at infinity will be 0. there's nothing to supply the capacitor with energy, so this is a natural response as well. So there are two ways. We can either get the initial voltage here and the total expression Vc at t, and do a current divider. We get the expression of V0 at t, and then set t equal to 0 to find V0 at 0 plus. Or we can directly get the initial value of the voltage here across the capacitor, and at time equal 0, switch this capacitor with a voltage source of value equal to V at 0 minus, because the voltage across the capacitor is continuous. So I'm gonna do both methods. So method one, this involves getting the entire expression of V0 at t. We need to get the voltage across the capacitor, which is going to be V0 exponential minus t over tau. This is the voltage across the capacitor, with tau being RC. Okay, so initially, before switching, we have the circuit looking like this: plus minus 180, a short circuit, resistor 50 ohms. This is an open circuit, which is the capacitor, which is what I need exactly, V at 0 minus. Okay, we have 40 ohm, and we have 10 ohm. This is at time equals 0 minus. Okay, so I can do some simplifications to make my life easier. We can, because this is an open circuit right here, I can remove this entire wire. So I can do this and say that the voltage across the 50 ohm resistor is V0 minus, which is the voltage of my interest. Another thing I can do is I can remove this and make the circuit look like this, essentially, because I had extra wires above that are going like this, which are really not needed. So I can make the circuit look like this. Here we have a 40 ohm resistor. Let me do it better. Here we have a 40 ohm resistor, and I need the voltage across the 50 ohm resistor. So what I can do is exactly voltage divider, because the voltage from here to here is 180, and this 180 is getting split between 50 and 10. So the voltage divider formula will be 180 multiplied by 50. I want the voltage across the 50 ohm over 50 plus 10, which is the total. This is going to be V at 0 minus. So V at 0 minus will be equal to 180 50 over 60. This is going to be 150 volts. So I found the first unknown in my solution, which is 150. Okay, and still I need tau, and tau I get it by R equivalent times C, where R equivalent is the resistance seen by the capacitor after switching. R equivalent. So it looks like this. Here we have a 40K, and here we have a 10K. And I want to see the resistance like this, R equivalent, looking from the capacitor. So we see immediately by inspection that the 40K and the 10K are in series. So what I can do is say that R equivalent is 40K plus 10K equal 50K. Okay, and so I'm going to take it right here. Tau, this is equal to R equivalent C. So 50 times 10 to the 3 times the value of the capacitor, which is 1 milli. So 10 to the minus 3, which is 1 milli. This is equal to 50. Okay, and so tau is equal to 1 over 50 hertz. Okay, so let's add another page. So Vc at t is equal to V0 minus, V0 minus is 150 exponential minus t over 50, determined in volts. So what I can do now is a voltage divider, because I got the voltage across this capacitor. So I can do a voltage divider and find this voltage in here. So the circuit looks like this. I have this capacitor. This is 40 kilo, this is 10 kilo. This is plus minus VC at T, which I calculated just now, which is this. So I can do a voltage divider to find V0 at T. So V0 at T, this is equal to VC at T times 10 over 10 plus 40 in kilo. Therefore, it's 150 times 10 over 10 plus 40, which is 30 exponential minus T over 50 volt. This right here is 150 times 10 over 10 plus 40 from the voltage divider. So finally, V0 at 0 plus, I can substitute 0 instead of time, so I get 30 exponential minus 0 over 50, so 30 exponential 0, so 30 volt. Now this is method 1, which involves getting the entirety of the voltage across the capacitor. I have a more direct method, which is method 2, which involves turning the voltage source, which involves turning the capacitor into a voltage source. So what I can do is calculate the initial voltage across the capacitor, which is V at 0 minus, and at time equals 0 plus, right after switching, I can substitute this capacitor with a voltage source. So let's do this. At time t equal 0 plus, okay, I can replace the capacitor with a voltage source V0 minus, which is equal to 30 volt. I calculated this before in here. So I did, sorry, not 30, this is 150, my bad. This is 150, not 30. I calculated this before, so I replaced the capacitor with a voltage source at time equals 0 plus right at switching. Here I have a 40k and here I have 10k. And we're doing this analysis at time equals 0 plus, remember, so whatever value I get in here, it's a value at 0 plus. So this voltage right here, which is V0 at 0 plus, by voltage divider I can do 50, this is at 0 plus, 50 times 10 over 10 plus 40, which again is going to be 150 over 6, which is 30 volts. Okay. Over 5, not over 6. 150 over 5, which is 30 volts. There are two ways to get this answer, and our answer is C. I prefer method 2 because it's more direct. I don't have to get the entire expression of my voltage at the capacitor. I can directly just substitute the capacitor for a voltage source and get V0 at 0 plus directly. Okay, so in problem 3, we have this circuit and we're asked to find the energy in joules stored in the 40 millihenry inductor at time equal to infinity. Here we have two inductors in parallel after switching. So after switching, I can imagine the circuit being like this. We have these disconnected and we have these two inductors in parallel. So if I want the expression of the current in them, I have to worry about tau, which is L over R equivalent, but L is L equivalent by itself. I can do L for one inductor and forget the other. So I need to do L equivalent, get whatever values I need from L equivalent and transform them back into two inductors parallel with each other. So this is the strategy. So before I do L equivalent, I need to get some initial values, which are the current going in this inductor at time equals 0 and the current going in this inductor also at time equals 0. So for L1 before switching, we had this network with L1, okay? But before switching, we had a steady state value. So instead of the inductor, I'm going to put a short circuit and I need this current in here. But the 1 kilo ohm resistor is short circuited by this inductor because we have a steady state. So this value of the current in here, this is going to be exactly 11 ampere. So the initial value of the current in the first inductor, the initial value of the current in the first inductor will be 11 ampere. So for the network in L2, we have this scenario. The current source is 2 ampere, 1 kilo ohm, and the inductor is also short circuited. And we need this current in here. I. But also in this case, the 1 kilo ohm is short circuited by the inductor, so we have the current, the entire current of the source flowing in the short circuit. So I will be exactly that of the source. So we have, this is 11 ampere going down and this is 2 ampere going up. So if we need to do the equivalent circuit, it's going to look like this. This is L equivalent. And this is the resistor that we have, which is 1 kilo ohm. The initial value of this current will be, look here, we have L1 with current going down and L2 with current going up. So what I can do is 11 minus 2 will give me the current going downwards. So this current going down, this is equal to I equal 11 minus 2, which is 9 ampere. We start with 11 minus 2, 11 because we're going down, so the direction of our current is down. Okay, and L equivalent, because we have two inductors in parallel, which are 40 and 10, L equivalent will be 40 times 10 over 40 plus 10, which will be equal to 8, I believe. Yeah, this is equal to 8 millihenry. Okay. Yep. So what I can do is, get the current in the L equivalent, because I know that the current is continuous. So whatever I get for I0 minus is equal to I0 plus. So the expression of I, I'm gonna call it equivalent of T. This is equal to 9, which is the initial current in the equivalent inductor, exponential minus, now I need tau on the side, I'm gonna do tau is equal to L equivalent over R equivalent. This is equal to 8 times 10 to the minus 3 over 10 to the 3, 8 times 10 to the minus 6. This is tau, so 1 over tau, this is equal to 1 over 8 minus 6. This is going to be 125,000 hertz. So here I can do minus 125,000 T. This is the expression of the current in the inductor. But I have a simple problem or a simple thing that I need to go back to the circuit I had originally. So I need to go back to L1 and L2 being in parallel. So I can't really use much of this equivalent current, but what I can do is get the voltage across this equivalent inductor, and if I go back to this parallel connection, I'll have this voltage, the same voltage in here. Let's call it the equivalent at T. Because everything is in parallel, so the voltage across the parallel inductors is equal to the voltage across each inductor separately. So I can get the voltage across the equivalent inductor V of T. And this is going to be L di by dt, L equivalent. And I is I equivalent, which we calculated just now. Okay, L equivalent is 8 times 10 to the minus 3. Di by dt, we have 9. We multiply this by minus 125,000, right? And then multiply this at last by exponential minus 125,000 T. Okay, if I multiply these, what do I get? I get 8 times 9 times minus 125, whatever. We have V equivalent is equal to minus 9,000 exponential minus 125,000 T expressed in volts. Okay, so I got the voltage in here, and this voltage, this is exactly equal to the voltage across across L1, which is the 40 millihenry, which is the value I'm interested in, the inductor I'm interested in calculating the energy in. So this voltage right here is V equivalent at T. Okay, and this is a good start. If I have the voltage, I can get the current, and we know from the formula sheet, and as we know حتى بلا formula sheet يعني, the energy across the inductor is half Li square. So if I evaluate this current at infinity, I'm gonna get the energy at time equal to infinity. So I need the current in the L1, inductor, but I have the voltage. But easily, if I have the voltage across the inductor, I know that the current will be 1 over L, in this case L1, integral, right, Vx dx, this is going from 0 to t, by the way. This is V equivalent, which we calculated, okay? Plus some initial value, which is I'm gonna call it I1 at 0. If we have this V equal L di by dt, if I want the I get L to the other side, and then do an integral. So 1 over L integral of V plus some initial condition, which is the constant of integration, a boundary condition. So I will be 1 over 40 times 10 to the minus 3. Okay, the integral, I'm gonna do this immediately. So the integral, this is minus 9,000 divided by minus 125,000 exponential minus all of this t, okay, evaluated from t to 0, this is in terms of x, by the way, plus some initial value of the current, which is equal to, now notice in here we have the voltage plus minus, so we need the current going like this. So the initial value is exactly 11 ampere, so we have the correct direction of the current, 11 ampere. Okay? This is equal to 140, or 100 over 10 power minus 3, so I'm gonna do this calculation in here, times 9,000 over 125,000, this is 1.8, exponential minus 125,000 t, I'm doing the evaluation of the integral boundaries, minus exponential at 0 is 1, plus 11 at the end, so this is equal to 1.8 exponential minus this thing, minus 1.8 plus 11. Okay, but I need the energy at time equal infinity, so I of infinity, so I take time goes to infinity, so the exponential will die out, so minus 1.8 plus 11, this is 9.2. The current at infinity is 9.2. So I'm gonna go back. The energy is half Li square, but I got I at infinity, so half times 40 times 10 to the minus 3 times 9.2 square, so 0.5 times 40 times 10 to the minus 3 times 9.2 square, this is going to be, the energy is 1.6928 joules. So the answer is going to be C. This is an example where we have two components in parallel, be it inductors or capacitors, in this case an inductor. Two inductors in parallel, we do the equivalent combination of both. We get the current in the inductor. If we have a capacitor, we get the voltage in the capacitor. Why? Because the current in the inductor is continuous, while the voltage in the capacitor is the one which is continuous, not the current. In the case of the inductor, current is continuous, so we get the equation of the current. From the equation of the current, we get the voltage, because in the parallel connection, they all have the same voltage. After we get the voltage, we go back again to the current in one of them. We evaluate this current at infinity, and then do half Li square of this value. We get our answer. Okay, in this problem, in problem 4, let IS be 13.6 ampere. Okay, the expression of the voltage Vt is given by this formula. So we have a constant alone plus a constant times an exponential. We need to find the value of K2. Now in the back of our minds, we know that if we have a first order response circuit, we don't have a capacitor, we only have an inductor. So this is chapter 7. In the back of our minds, we know that the expression of the voltage or the current, any quantity basically, is, let's do this in general. X of t, this is equal to x at infinity plus x at 0 plus minus x at infinity exponential minus t over tau. Now for the sake of this problem, I'm not gonna care about the exponential t over tau. We only need this, the coefficient of the exponential, which is K2 in our case, which is V at 0 plus minus V at infinity. So our problem is divided into two parts. We need this at time equals 0 plus and at time approaches infinity, and we get K2, the expression of K2. Okay, sorry about that. Okay, so we agree that K2, this is equal to V at 0 minus V at infinity, at 0 plus. Now, if I get the voltage here at time equals 0, this is not going to be a continuous value because the resistor doesn't have a continuous current or a continuous voltage across switching. The capacitor have a continuous voltage at switching, while the inductor have a continuous current across switching. Here I have an inductor, so it's in my interest to calculate this current in here. So I need this current at time equals 0 minus, and then I'll see what will happen at time equals 0 plus. But basically I need the current at I equals 0 minus because it is equal to I at 0 plus. Actually, let me write this in here. I am sorry. So K2 is equal to V infinity minus, sorry, V at 0 plus minus V infinity, and we need V0 plus, so we need I at 0 minus. So at time equals 0 minus, I draw the circuit before switching. So we have plus minus 120 volt, a resistor 20 ohm, this 100 ohm, which is the value of my interest, and here I have a short circuit. Now I need this current, let's say that's going in this direction, for example, or actually let us take it, the current going in the opposite direction. Let's say that I need the current right here, I0 minus. It doesn't matter really, there will be a minus sign, that's the only difference. I at 0 minus. Okay? Now, the 100 ohm is short circuited, so I can delete this 100 ohm because of the short circuit. So I have the circuit looking like this, and I know that I at 0 minus, this is going to be 120, which is the voltage over the resistance. This is equal to 6 ampere. Okay? Now, I got the initial voltage across the inductor, and it will carry over to 0 plus. So at t equals 0 plus, right at switching, we switch the circuit and we have this current source. Sorry, we have this current source, 13.6. Okay. The resistor right here is 150 ohm. Okay. We do the switching. This is 100 ohm, and at time equals 0 minus, the inductor will become a current source, but the current source is in this direction as we calculated it. So this is I at 0 minus, which is equal to I at 0 plus because it's continuous. What I need now is to find the voltage across the 100 ohm capacitor, which is 100 ohm resistor, which is V0 plus. Okay? Now, okay, I can do multiple things, including source transformation maybe, or a KCL. Actually, a KCL is very easy. Okay? So, let's call this node V0 plus, and let's do a KCL. So, flowing into the node we have minus 13.6 plus V0 plus over 150 plus V0 plus over 100 plus the initial value of the current, which we got it to be 6. That's equal to 6, so plus 6. All is equal to 0. Now I can solve the equation for V0 plus. I'm gonna do this. So 13.6 minus 6. So V0 plus over 150 plus 1 over 100 is equal to 7.6. Now carry this to the other side. We have 0.6 divided by 1 over 150 plus 1 over 100. So V0 plus will be 456 volts. Now this is V0 plus. I'm done with it. Now I need V at infinity. Now V at infinity, so after switching, we have a steady state at infinity. Everything is DC, and the inductor can be replaced by a short circuit. So let's draw our circuit at infinity. So T approaches infinity. We have this 13.6 amperes, 150 ohms, 100 ohm, and a short circuit in here, right? But this short circuit will absorb all the current because the current will move like this and see an equivalent resistor in here, but will continue to the short circuit anyways. We have a short circuit, so the 100 ohm and the 150 ohm are shorted, so no current flow in here, and all the current flow in the short circuit, so the voltage across everything is 0. So V at infinity is simply 0 volt. So finally K2 is equal to V at 0 plus minus V at infinity, which is 456 minus 0, which is exactly 456. So if you go to the options, we see that the answer is answer D, 456. So the strategy is that we got the current across the inductor because it's continuous. We got it at 0 minus before switching. And before switching, we have steady state, so the inductor is short circuited. So, and this I0 minus will be I0 plus, exactly the same. So right at switching, we replace the inductor by a current source, which is exactly I at 0 minus. We do our calculations and find V0 plus. We did KCL, or nodal basically. So nodal answers or KCL, same thing. We got V at 0 plus. Finally, we got V at infinity by doing steady state analysis. So instead of the inductor, we replace it by a short circuit, and we see that the 100 and 150 are shorted, so the voltage across all is 0. Finally, we do K2 is V0 plus minus V infinity, so K2 is V0 plus, and we get our answer. Okay, in this circuit, problem 5, we're given that Vs is 60 volt. We need to find I at 0 plus. I at 0 plus, which is this current right here. I can do a similar process, which is get the voltage here, because the voltage is continuous, so V at 0 minus, carry it on to time equals 0 plus, so replace the capacitor with a voltage source with value V0 minus. Get my current at I at 0 plus, so at time equals 0 plus, this will be I at 0 plus. And the problem is done. Basically, I only need I at 0 plus. I don't need tau or anything else. Okay, so this is my strategy. So before switching, my circuit was looking like this. Plus minus 60 volt, 5 kilo ohm, 10 kilo. And this is an open circuit. So the voltage in here can be expressed by a voltage divider. So I know that V at 0 minus, this is equal to the voltage across the 10 kilo ohm resistor, so 60 times 10 over 10 plus 5. So V at 0 minus, this is equal to 60 times 10 over 15, so 40. This is V at 0 minus. Now, right after switching at time equals 0 plus, I do the switching and replace the capacitor with V0 minus source. Like this. This is 40 volt. Okay. Yeah. This is resistor 40k ohm. This resistor is 10k ohm, and this source is minus plus 120 volt. And I need this current flowing like this. I can do also nodal. Nodal is easy in here. Let me add another page. Nodal is easy in here because we have a common node between all. We have this node in here, let's call it VA, and the value of VA is exactly this 40 volt source. Because the only thing connected between this node and the ground is this source. So we can say that VA is equal to 40 volt. And the current, this current in here, which is I0 plus, flowing in this direction, this is equal to I at 0 plus my starting node, which is VA, minus my ending voltage in here, which is this source, minus 120. I put the minus 120 because it's inverted. Normally the plus is above. So if you can do a KVL basically. So this is minus plus, right? So minus VA plus 10 kilo I0 plus minus 120. This is equal to 0. Rearrange the equation, I'll get this exactly. So 10 kilo ohm. So I at 0 plus is equal to VA is 40 plus 120 divided by 10 kilo, right? So 40 plus 120 is 160, divided by 10,000 will be I at 0 plus is equal to 0.016 ampere, which is also 16 milliampere. So 16 milliampere, if we see our answers, we get answer B. Okay, basically let me simplify what I did in here. So this equation comes from a KVL. So if I do a KVL like this, I'm gonna get minus VA plus 10 kilo I at 0 plus. If I continue the KVL, I'm gonna hit the minus 120 is equal to 0. So 10 kilo I at 0 plus, this is equal to VA plus 120. Now get this to the other side here. I'm gonna get divide by 10k, which is exactly this formula. Okay, and we got our answer. Basically this is the same exact strategy as problem 4, but instead I get the voltage across the capacitor because the voltage is continuous across the capacitor, while the current is continuous across the inductor, which is the case in problem 4. So here in problem 6, we have in a series RLC circuit, the current expression, so the expression of the current for time equals 0 is I of t equal to I at infinity plus these terms in here. Okay, these terms, where S1 is equal to minus 100 and S2 is equal to minus 140. Now I have an RLC circuit, so I have in the same network an inductor and a capacitor. So I know that I'm in chapter 8 and I'm in series RLC. So and I'm given the equation of the current, which is I at infinity plus constant exponential S1t plus another constant exponential S2t. So from the formula sheet, I recognize this formula and I see that it's an overdamped response from the RLC circuit. I'm given S1 and S2, and I know that S1 or S2, this is equal to minus alpha plus or minus square root alpha square minus omega 0 square. This is included in the formula sheet, also in this PDF. Okay, now I need to decide which one is which. So is the minus 100, I have a minus in here or a plus in here, for example, right? I need to decide if S1 gets a minus sign or it gets a plus sign. So I notice that S1 is greater than S2 because minus 100 is greater than minus 140. Therefore, S1 is equal to minus alpha plus omega plus square root alpha square minus omega 0 square. Why did I choose plus? Because I have a negative value and I add to it something positive. So it's negative, but now it increases, right? Counter to S2, which is minus alpha minus square root alpha square minus omega 0 square. So I have something negative and I subtract something positive from it, so more negative. So I know that S2 is less than S1, therefore I choose the minus sign for S2 and the positive sign for S1. And basically I have S1 and S2. So this becomes two equations to unknowns basically. I know that this is minus 100 and this is minus 240. Now there are two ways to solve this system. One way is to add them, another way is to multiply them. Let's start with addition. So if I add them, I get, no, this is 120. Okay, 140. So if I add these two equations, I get minus 240. This is equal to minus 2 alpha. Now the square root cancels, so this cancels with this, these two. So plus the square root and minus square root cancel, so I'm left with this, and alpha, this is equal to 240 divided by 2, which is 120. I got one of the unknowns, I can get the other simply by replacing in the equation, so I choose one of them, so minus 100. This is equal to minus alpha, so minus 120, plus the square root 120 square minus omega 0 square. Now isolate omega 0 square, I get 120 square minus omega 0 square. This is equal to 120 minus 100, all of it square. Now, so omega 0 square, this is equal to 120 square minus 120 minus 100 is 20, so 20 square. Remove the square and do a square root on the other side. Omega 0, this is equal to, basically I isolated omega 0. So 120 square minus 20 square, this is equal to 118.32 radian per second. So if I look at my answers, this is going to be answer A. So two equations, two unknowns basically. Another way to approach this is multiply them, multiply these two equations. If I multiply these, I get S1, S2, the multiplication is equal to minus alpha plus square root alpha square minus omega 0 square. Let me do this. Okay. Into minus alpha minus square root alpha square minus omega 0 square. Okay. Distribute. I have alpha square minus alpha square root whatever plus. Okay. So plus. Yeah, minus and minus will cancel, so this minus will cancel with this minus right here, so plus. So I'm left with minus alpha square root whatever. Minus and minus will remain, so minus, remove the square root alpha square minus omega 0 square. Right, now plus alpha square root and minus alpha square root will remove each other, so I have alpha square minus omega 0 square. So this is equal to alpha square minus alpha square plus omega 0 square. Alpha and alpha cancel. I'm left with S1, S2 is equal to omega 0 square. So omega 0, this is equal to square root S1, S2, which is square root 100 times 140. So omega 0, this is equal to 100 times 140, which is 118.32 radian per second. So our answer is also answer A. So we have two methods, either to add the system of equations or multiply them. We get the same answer basically. And solve using whatever method you like. Okay, in problem 7 we have the following circuit. We're asked to. So in problem 7 we have this circuit and we're asked to find the expression of V0 of t for time greater than 0. So V0 of t is the voltage across the inductor, and we need to decide if this circuit is parallel or series connection. Now to do so, we consider time after switching. So the switch is here, and we notice that the capacitor and the inductor are in parallel, but we need to see the resistor. Well, we have a capacitor parallel with an inductor parallel with this resistive network, but I really don't know how to deal with this. So maybe I can reduce the entirety of this into R equivalent, just one R. So how do I do this with an dependent source in here? We can do R Thevenin, right? We can do Thevenin analysis. So before I start with any of the equations, I know beforehand that it's a parallel connection. Maybe I can apply R Thevenin in here. So let's see. This is the shape of the resistive network, and I need to determine the Thevenin resistance seen by the parallel inductor and capacitor. So here we have the 50 ohms, here we have the 60 ohms, okay, and I phi is flowing like this, and we need to see R Thevenin like this, seen by the capacitor and the inductor. So one way to do this is to put a test voltage here, V test, and an I test like this, and say that R Thevenin is equal to VT over IT. So I'm basically testing the circuit, seeing if I apply a voltage, what would be the current response, and the division of these two will give me a resistance seen by the inductor and capacitor to the right. So I need VT over IT, this ratio. So let's write some equations. Let's say that, let's do basically a nodal, fine. If we do a nodal in here, let's say this is VA and this is ground. Immediately we can say by inspection that VA is equal to VT plus 10 I phi. Why? Because if we do a KVL, if you consider this plus minus VA, and we do a KVL like this, we get minus VT minus 10 I phi plus VA equal to 0. So rearranging the terms, we get VA equal VT plus 10 I phi. So basically the only things connecting the ground to VA are some sources, which are VT and 10 I phi. Okay, if we write the equation, the KCL, we get that minus IT plus VA, but VA is VT plus 10 I phi, over the resistance, which is 150 kilo, no, just 150 now without kilo, okay, plus VA over 60, but also VA is VT plus 10 I phi divided by 60. Now all is equal to 0, but now I don't know what I phi is, so I need to get an equation that only relates VT to IT, so that I take the ratio. So I can say that I phi is a current divider, yeah, because if I have IT flowing like this, it's also flowing in here, IT, and it's dividing into minus I phi and some current in here, I don't care. So I can do a current divider in here to figure out I phi. So current divider, so minus I phi, which is flowing down into the 60 ohm, is equal to IT times the other resistor, so 150 divided by the sum. 150 divided by the sum of the two, so 150 plus 60. So we get that I phi is equal to minus, if we do the calculation, 150 over 150 plus 60, 5 over 7 minus 5 over 7 IT. Substitute back, we get minus IT plus VT minus 50 over 7 IT divided by 150 plus VT minus also 50 over 7 IT over 60 is equal to 0. Now, if you want, you can let VT equal some number, maybe 12 volts, and solve for IT. You can do this, because whatever you pick for VT, you'll get a different answer for IT, and ultimately R Thevenin is equal to VT over IT, but whatever you change in here will also be changed in here, so you get an equal ratio. Anyways, if you choose any value, this is to make your calculations easier, so you don't need to take a ratio of anything. But I'm gonna do it in general. You can also do it in general, and you can take any value you want, like 12 volt, 10 volt. It will make things easier. In my case, I'll do it in general. So we have VT into 1 over 150 plus 1 over 60, okay, minus IT into 50 over 7 over 150 plus 50 over 7 over 60 minus IT, all equal to 0. So at last we get VT over IT. This is equal to 1 over 150 plus 1 over 60. So we ultimately get VT over IT. This is equal to 1 over 50. No, sorry. So ultimately we get, VT over IT. This is equal to minus 1 minus 50 over 7 killa over 150 minus 50 over 7 all over 60 divided by 1 over 150 plus 1 over 160, sorry, 60 alone, okay? This will be I Thevenin, which is equal to, now 50, now this is a minus sign, but I really don't care. I can take an absolute value, right? So here it's 50 ohms. So basically what I mean is that I get a negative sign in here, but a positive sign in here. I really don't care. I can put IT in here. It doesn't change anything. So basically, if you want, you can take R Thevenin is equal to positive values. If you get IT is a negative number, you can like close your eyes and nothing will happen. No. So we ultimately get VT over IT. Now, if I get the ITs to the other side and divide everything, we get 1 plus 50 over 7 كلها over 150 plus 50 over 7 all of it over 60 divided by 1 over 150 plus 1 over 60. This will give me R Thevenin, which is equal to 50 ohms if we plug this into a calculator. So we get R Thevenin equal 50 ohms, and our circuit after switching will be like a capacitor, an inductor, and a single resistor, which is 50 ohms. So let's do this. So after switching, our circuit looks like this. After switching, we have the capacitor, 8 microfarad, an inductor, 51.2 millihenry, and finally a resistor, which is 50 ohms. Like this. So I reduced this entire network into just a single resistor, like this. This is a 50 ohm resistor. Okay, now I clearly notice that we have a parallel connection between everything. So I use the parallel connection formulas. So alpha is going to be 1 over 2 RC, which is equal to 1 over 2 times 50 times 8 times 10 to the minus 6, because it's 8 microfarad, which is equal to 100 times 8 times 10 to the minus 6. This is equal to 1250. Okay. Omega 0, this is equal to 1 over square root LC always. By the way, these two formulas are in the formula sheet. This is equal to 1 over square root L, so 51.2 times 10 to the minus 3. The capacitor is 8 times 10 to the minus 6. All of this is equal to, so if we do the calculations, 51.2 times 10 to the minus 3 times 8 times 10 to the minus 6, we get 1562.5 radian per second. So I do a simple comparison. I see alpha and omega 0, which is greater than which? Obviously, omega 0 is greater than alpha. So we have the oscillations are greater than the dampening effect. So overall, if you look into the formula sheet, this is the case of underdamped response. The oscillations are greater than the damping effect. So an underdamped response, our solution will be V0 of t is equal to V at infinity, V0 at infinity, plus exponential minus alpha t into B1 cosine omega d t plus B2 sine omega d t. So we need to figure out this quantity. I know alpha, okay? I need to figure out B1, I need to figure out omega d, and I need to figure out B2. Luckily, we have a formula for omega d. Omega d is square root omega 0 square minus alpha square. So this is equal to square root 1562.5 square minus 1250 square. Overall, omega d is equal to, so we do this, 0.5 square, right? Okay. Minus this square will get 937.5 radian per second. Okay, we figured out omega d. Now what about V0 at infinity? So again, at t equal infinity, well, the capacitor is an open circuit, the inductor is a short circuit. This inductor, We have an open circuit for the capacitor, the inductor is a short circuit, and we have a resistor. Well, the voltage in here is 0. It's a short circuit. Basically, nothing is giving me energy. There are no sources left at t equals 0, at t equal infinity. So I don't have a supply of energy, so I get the voltage is equal to 0 anyways. Right? So let's add a new page. Okay. So V at infinity will be equal to 0. Nothing is giving a voltage. I don't have a voltage connected to my network at t equal infinity. So V0 is equal to 0. Fine. I'm left with B1 and B2. Now, how do I get B1 and B2? Here's B1, here's B2. I need to get these two values. I get them from two quantities, which are V0 at 0 plus from the initial condition, and I get them from dV0 at 0 plus by dt. Basically, I find the value of the voltage at 0 plus, and I find the value of the derivative of this voltage at 0 plus. From the formula sheet, I know that dV0 at 0 plus by dt, this is going to be omega d B1 plus alpha B2. Okay, just let me check. From the formula sheet given, omega d B2 minus alpha B1. Okay, so omega d B2, so we flip this, omega d B2 minus alpha B1, given in the formula sheet. And I know V0 plus because I can replace in here for time equal to 0. If time equal to 0, this will be 1. Cosine 0, this will be also 1, so B1 will survive. Sine 0 will be 0, so B2 is cancelled, so we only get B1. Now, in the normal case, I also get V0 at infinity because it's left outside plus B1, but we agreed that this is 0. I don't have anything giving me a voltage at time equal infinity, so I'm left with B1. So what's V0 at 0 plus? We look at our circuit in here, and I see that if I calculate the voltage across this capacitor at time equal 0 minus, I can carry this over to V at 0 plus because the voltage is continuous across the capacitor, and this will be my V0 plus for the entire circuit because everything is in parallel. So let me get V0 minus for the capacitor. We can simply do it by inspection in here. So it's like a voltage source, a resistor, another resistor, and an open circuit. So basically I need the voltage across this resistor, which is a voltage divider formula. So 50 times 4 over 4 plus 6. Hopefully this is intuitive. So in here, V0 at 0 plus, this is equal to 50 times 40, I guess. 50 times 4, over 6. 50 times 4 over 6 plus 4. This is going to give me 50 times 4 over 10. This is going to give me 20. So the initial voltage is 20. So B1 is equal to 20, which is V0 at 0 plus. Great, I got one equation. Now for the other, I need dV0 0 plus by dt. Now if I check my equations, I see that to get the derivative of the voltage, the easiest equation is the current in the capacitor. This is equal to C dV by dt. So in my circuit, if I figure the initial current in the capacitor, I can easily figure the initial derivative of the voltage, initial change in the voltage. So I need to figure out IC. One way to figure out IC, now if you notice here we have an open circuit before switching. We can't really do this analysis because the current in the capacitor is not continuous. So I can't find the initial current in the capacitor from analyzing at time equals 0 minus before switching, because the current in the capacitor is not continuous. The current that is continuous is that of the inductor in here, right? So I need the current in the inductor, but we noticed that before switching, this was disconnected. This was disconnected from the capacitor. So we had the inductor being a short circuit, steady state, and we had this effectively 50 ohm resistor. So there is nothing in here, I equals 0. There's nothing feeding current to my circuit because we have this switch at B disconnected. There is nothing in here. So IL at 0 minus is 0, and oops, sorry. So in here IL at 0 minus, this is equal to 0. Okay. So maybe I can do a KCL in here, and I can call this V0 at 0 plus, because this is right at switching. So after switching, so at time equal 0 plus, I can do a KCL. So I need to figure out the current in here. I see the current in here is 0. We agreed on this. And the current in here is basically V0 plus over 50. So I see. Let me add another page. Okay, so KCL, this will give me IC plus IL at 0 plus, this is 0 from I0 minus, plus V0 at 0 plus, which is the voltage at that node over the resistance R, all is equal to 0. So IC, this is equal to minus V0 at 0 plus, which is 20 over R, which is 50. In amperes. So IC is equal to C dV by dt. This is at time equals 0 plus, by the way. So dV by dt at time equals 0 plus, this is equal to IC at 0 plus divided by the capacitance. So minus 20 over 50 divided by the capacitance value, which is 8 times 10 to the minus 6. If I do this, I get, okay, so minus 2 over 5 divided by 8 times 10 to the minus 6, minus 50,000 volts per second. Okay, I got dv0 at 0 plus by dt at time equals 0 plus, and I can substitute it in here. I know omega d, I know alpha, I got b1 just now, so I can get b2. So in here, minus 50,000, this is equal to omega d b2. Omega d is 937.5. So 937.5 b2, and then plus alpha b1, but alpha is 1250, right? Plus 1250 times 20, right? So this is dv at 0 plus by dt. This is omega d, this is alpha, and this is b1. So if I arrange my equations, I get b2, this is equal to, let me do the arrangement, so minus 50,000 minus this divided by 937.5, I get the value of minus 80 volts. And so I can put all the constants in my solution. So v0 at t, for any time t, not at 0 plus, for any time t, this is equal to v0 at infinity is 0, so I don't include it, exponential minus 1250t into b1, which is 20, cosine omega d, so 937.5t, minus 80, which is b2, sine 937.5t, and this is my answer in volt. Now, in the circuit above, I have IS is equal to 8 ampere. Find the expression of IT for time greater than 0. Now, I see from this that if I close the switches, right, and this is open at time equals 0 minus, at time equals 0 plus, this is open and this is closed, I have the series RLC. They're all in series. So I use the series equation. So alpha is equal to R over 2L, and omega 0, this is equal to 1 over square root LC. R over 2L, simply R here is 500, I don't need to do a Thevenin, there is only one resistor. 2 times 400, so 0.4. This will give me 500 over 2 times 0.4, 625. Omega 0, which is 1 over square root LC, so L is equal to 0.4, times my capacitor, which is 10 times 10 to the minus 6, This is equal to 1 over square root 0.4 times 10 to the minus 5. So 500. So alpha is greater than omega 0. So the damping is greater than the oscillations. I have an overdamped response. And I know I need the current. So my current is I at infinity plus some constant, I'm gonna figure it out later, S1 of t plus A2 as exponential S2 of t, where S1, S2 is given by minus alpha plus or minus square root alpha square minus omega 0 square. So from this, if I do the calculations, I'm gonna get minus 625 plus square root 625 square minus 500 square, either negative 250 or I get minus 1000. So this is S1 and S2. Let me add another page. Not this one. This is S1 and S2. Now, I at infinity, let me get I at infinity anyways. So at time equals 0 plus, I do the switching. And I notice that after the switching, I don't have the source giving anything to my circuit. So essentially my signal will die out, and at infinity nothing will remain. So I at infinity, this is equal to 0. Because I don't have a source after switching. Nothing is giving energy to my circuit. And an overdamped response looks like this. So I have a strong exponential downward, and it will go to 0 eventually. So unless I have a source. If I have a source, it will steady out at some level. I at infinity. But this is not the case in here. Okay. So if I at infinity is 0, the thing that remains is that I get A1 and A2. So let me write this. IT is equal to A1 e power minus 250t plus A2 e power minus 1000t. And let me draw the circuit after switching. So this is the capacitor, this is the resistor, this is inductor. 10 microfarad, 510 micro, okay, 500 and 0.4 Henry. Now I need to get the constants A1 and A2. Okay, so my circuit looks like this, and I need to get A1 and A2. So the way I get them is from V0 plus, or actually I need the current, not the current, I at 0 plus, and the derivative di at 0 plus by dt. Now I know at I0 plus, if I substitute 0, I get A1 plus A2. If I substitute 0 in here, 0 in the exponential, which is 1, 0 in the exponential, which is 1, so I get A1 plus A2. di 0 plus by dt, from the formula sheet for the overdamped response, this is S1 A1 plus S2 A2. Now my job is to get this value from the circuit, not from the formulas. So from the circuit, I0 plus, I can get it from the current, from the inductor, sorry. So from the inductor at time equals 0 minus, so at time equals 0 minus, I get I at 0 minus, which is equal to I at 0 plus, so I can carry it over in the inductor. So, okay, so if I label my current I0 plus across the inductor, which is exactly the same as I0 minus, because the current in the inductor is continuous, okay, and I consider T0 minus before switching, so this switch is closed initially, and this switch in here is open, so I don't have anything in here, so this is cancelled, this resistor. So the current that's flowing like this, I at 0 plus, this is equal to the voltage 200, which is my source, divided by 50, which is 20 over 5, which is 4 ampere. So I get back to my equations and put I0 plus equal 4 ampere. That's equation 1 in my system. Now I need the derivative of this current at 0 plus. Okay, now I need the derivative of the current. A good formula to start from is that V equal LdI by dt, which is the voltage across an inductor. If I know the voltage across my inductor, I can get the expression of di by dt easily. So how can I find the voltage in a series? How can I get the expression of di by dt in my circuit is that I need to find the voltage across the inductor. And to find the voltage across the inductor, the best way, if I have an RLC series connection, is to do a KVL, right? So if I do a KVL like this, I need to find the voltage across the capacitor before switching, and, well, I have already I0 plus, so I0 plus times 500 will give me the voltage across the resistor, and I need this voltage right here, which is VL at 0 plus, if you wish. Okay, so I need also this voltage right here, which is VC at 0 plus. Now from the circuit, before switching, okay, I have this capacitor with this branch in here, the current source and the resistor. What I can do is that I can do a source transformation. So I'm gonna write it in here. This is going to be equal to minus plus. The value of the voltage is 8 times 100, so 800. This is source transformation, okay? The resistor is 100, and the capacitor is open circuited. So the voltage in here is minus 800. So if I flip polarity, minus plus, I get 800 volts. So down here, I flip the polarity, minus plus 800 volts. Now I can do this KVL right now. So I get minus 800 volts across the capacitor, plus 500 times I at 0 plus, so times 4, plus VL at 0 plus. All is equal to 0. So VL at 0 plus is equal to 800 minus 2000, which is equal to minus 1200 volts per volts. Yeah, just volts. Okay, this is my voltage. Now I know that across an inductor, the voltage is LdI by dt. So di by dt at time equals 0 plus is equal to this voltage at 0 plus divided by the value of the inductor, the inductance. So V0 plus, yeah, I just got right here, minus 1200 divided by the value of the inductance, 0.4. This will turn out to be minus 3000 amperes per second. So now I have two equations to unknowns. So I have A1 plus A2 is equal to 4. Equation number 1. Equation number 2 will give me minus 3000 is equal to S1 A1. S1 is minus 250. A1 minus 1000 A2. Now if I solve, let me add another page. If I solve for these two equations by putting them on the calculator, so mod 5 1, so I get A1 plus A2 is equal to 4 minus 250 minus 1000 minus is equal to minus 3000. I'm sorry, 114 minus 250 minus 1000 minus, okay, A1 is equal to 4 over 3, A2 is equal to 8 over 3, and the expression of my current is I of t is equal to A1 4 over 3 exponential S1, so minus 250 t, plus A2, which is 8 over 3 exponential S2 minus 1000 t. This is the expression of my current given an ampere. Okay, now we finished with chapter 8. Now let's start with chapter 12, which is the Laplace transform. So this is exercises on chapter 12. So in problem 9, consider a function f of t in the time domain, which is given by t cube exponential minus 2t. We need to find the Laplace transform and evaluate this Laplace transform at s equal minus 6. So the strategy in doing Laplace is that I need to make f of t similar to something I find in the formula on the formula sheet, or I need to shape f of t into something I can deal with, or something I can notice from the formula sheet. So f of t here is composed of t cubed multiplied by an exponential. I know that if I multiply with an exponential in time domain, it will correspond to a shift in the s domain. So I know that the inverse Laplace transform of this will be 1 over s, which is the Laplace transform of the unit step function, shifted by 2, so s plus 2. 1 over s plus 2. Remember that u of t transforms to 1 over s. If I multiply by an exponential, I will shift s by this exponential, so plus 2. But I also have t cube. Now, if I go and see my formula sheet, I notice that if my f of t is t power n, some function, it will transform to minus 1 power n, the nth derivative of the Laplace of this function in terms of s, or with respect to s. So if I have a polynomial t power n, not a polynomial but a term t power n, and I multiply it by some function f of t, what I will do is that I will do minus 1 power n. So if n is even, I ignore this. If n is odd, I add minus sign, and I do the Laplace transform of this f of t, and I do the derivative n times. So I need the nth derivative of this. So I need the nth derivative of this. So what I can do is that exponential minus 2t transforms to 1 over s plus 2, but I need to derive this or differentiate this 3 times. So capital F of s is equal to minus 1 power 3 d cube by ds cube, so derivative 3 times of 1 over s plus 2. So f of s is equal to minus d square by ds square. I will apply derivative once. This is equal to minus 1 over s plus 2 square. Minus and minus cancel. This is equal to d square over ds square 1 over s plus 2, all of it square. Okay, let me do derivative one more time. So this is d by ds of minus 2 over s plus 2 all cube. So what I did is that I took s plus 2 to the power of minus 2 and did a derivative. So I drop the exponent down, so minus 2 into s plus 2, and I subtract 1 from the exponent, so minus 3. And s plus 2 to the minus 3, I can put it in the denominator, s plus 2 to the power of 3. Okay. I do derivative one more time. So minus 2 times minus 3, same thing. I put this up, so s plus 2 to the minus 3. I drop the exponent and I subtract 1. So if I drop the exponent, I get the minus 3, divided by s plus 2, subtract 1 from the exponent, I get 4. So this is my f of s. So f of s, this is equal to 6 over s plus 2 power 4. Now we have s equal minus 6. So 6 over minus 6 plus 2 to the 4. 6 over 4 power 4. So 6 over 2 power 8, basically. 6 over 2 power 8 is Answer A. So 6 over 256. So what I did in here is that I noticed that my f of t can be written as t power something times a function that I can easily find the Laplace of, the Laplace transform of. And I know that the Laplace transform of an exponential minus at, it will go to 1 over s plus a. This is from the formula sheet, if you want, if you will. An exponential will cause a shift in s. And if I multiply both sides by, if I not both sides, if I multiply my function in time by t cube, I do derivative 3 times in here and multiply by a minus sign due to minus 1 power 3. So my answer is A. This is 6 over 4 cubed, so 6 over 256. So in problem 10, I have this function in time and I need the Laplace transform evaluated for s equals 0.5. And this reminds me of something. This is of the form f of t is equal to, if I look at my formula sheet, f of t is the integral from 0 to t of f of x dx. In my case, f of x, this is equal to exponential minus 0.5 x cosine 0.5 x. Now I know if f of t takes this form, f of s, it will transform to some f of s, which is equal to f of s divided by s, where f of s is the Laplace transform of f of x. Maybe I abused this notation a little bit, but basically what I'm saying is if I have f of t equal to the integral of 0 from 0 to t of g of x dx, f of t will Laplace transform, or the transform of f of t will be capital G of s divided by s. Basically what I'm saying. Okay. Sorry. dx. And let me erase all of this. So I know that my g of x, which is inside my integral, is this. So I need to find the Laplace transform of this. Well, I look into this g of x. I know the Laplace of cosine, and I multiply this function by an exponential, and I know that an exponential in time will result in a shift in s. So e power minus 0.5 x cosine. So let me do it in terms of t, just to make it easier. So exponential minus 0.5 t cosine 0.5 t. I know the Laplace of the cosine. This is equal to s over s square plus omega square. This is from the formula sheet. But also I multiply by exponential minus 0.5, so I do a shift. So I shift s by 0.5, which is the exponent basically. So I get this. Oh, omega is 0.5. It's the coefficient of the t inside the cosine. So if you want the angular frequency inside the cosine. So I have this form. This is the Laplace of cosine 0.5t shifted by 0.5 due to the exponential. Now I need to consider this integral, this form. So whatever I get, I need to divide by s. So this is my g of s. Divide everything by s and evaluate s for 0.5. So if I do so, my answer, this is going to be 0.5 plus 0.5, this is 1, divided by 0.5 plus 0.5, again 1, plus 0.5 square, all divided by 0.5. So I'm going to put 0.5 in here. So my answer is 1 over 0.5 into 1 plus 0.5 square. So 1.6, which is answer D. Okay, so in this problem, we're given f of t, which is a function in time, and I need the Laplace of the derivative df by dt evaluated at s equal 1. Now one way to do it is that I actually do the derivative. Of f of t, but this isn't optimal. It will consume a lot of time and maybe I'll get stuck in some places because I'm dealing with u of t and I'm really not comfortable with. Now I know that the derivative of u of t dt, this is equal to the impulse response, but still it's not very comfortable to deal with. So I propose another method, which is to notice that df by dt, this transforms into s f of s minus f at 0 minus. Basically, this is included in the formula sheet given in the exam. So I do the Laplace transform of f of t, I multiply it by s, and I subtract f evaluated at time equals 0 minus from the entire thing. So here we go. The Laplace of f of t, so f of t is equal to 4.2 u of t minus 4.2 u of t minus 1 plus exponential minus t sine t, and I need the Laplace of this. F of s is equal to 4.2 over s, u of t transforms to 1 over s, minus 4.2 over s exponential minus t. Now, why did I do this? Because I know that f of t minus a, u of t minus a, will go to f of s exponential minus as. This is included in the formula sheet. It's one of the rules, one of the functional transforms. So, in this case, f of t minus a is 4.2. It's a constant. I don't have a t. U of t minus a is u of t minus 1 in my case. So the exponential in here will be minus s. So minus 1s. So minus s here. And I do the transform as if it's not shifted. So it's like I'm doing the Laplace transform of u of t. But it's then u of t minus 1, so I introduce an exponential. It's one of the forms inside the formula sheet, inside the table. So this is the Laplace transform of that. And I do the Laplace transform of e to the minus t sine t. Now I know how to do the Laplace transform of sine t, and I multiply by an exponential, so whatever I get for the Laplace transform in here, I shift my s by 1 unit, so s plus 1, basically. The Laplace transform of the sine is omega, in this case 1, over s square plus 1, but I have an exponential, so I shift everything by plus 1, which is the power of the exponential. This is s f of s. Now I need this to solve my problem. It's okay, I multiply everything by s. I get this. Fine. F at 0 minus, let's evaluate it. F at 0 minus is equal to 4.2. The unit step function at 0 minus, 0. It's not activated yet. It's before 0, it's not activated. Minus u of minus 1, this is also 0. Plus exponential minus 0, so 1, sine 0. So again, all of this is 0. So 0 and 0, so f at 0 minus, this is equal to 0 altogether. So the Laplace transform in this case of df of t by dt, this is equal to f of s multiplied by s, so 4.2 minus 4.2 exponential minus s plus s over s plus 1 square plus 1. I evaluate this s equal 1, let s equal 1, because the question asks so. So 4.2 minus 4.2 exponential minus 1 plus 1 over 2 squared plus 5. So 4.2 minus 4.2 exponential minus 1 plus 1 over 5. This is 1. So if I evaluate this, I find that my answer is 2.8549. So if I look at the answers, here we go. 2.8549. Problem 12. I'm given f of s and I need f of t, specifically k1. Okay, so what I can do is partial fractions, right? Partial fraction expansion. So first of all, I need to factorize my denominator. So 18s squared plus 66s plus 90. This is equal to, if I find the roots of these, I'm gonna get s equal minus 1 and s equal minus 2. So my factorization is s plus 1. s plus 2, and s plus 3. Okay. So I can write f of s as, by partial fraction expansion, a over s plus 1 plus b over s plus 2 plus c over s plus 3. Notice here I have a proper fraction because the power of the numerator is less than the power of the denominator. This is my partial fraction expansion. Now I know that after I do Laplace inverse, I get a exponential minus t u of t plus b exponential minus 2t u of t plus c exponential minus 3t u of t. Why? Because I know that exponential minus as will go to 1 over s plus a. So if I have 1 over s plus 1, I get e power minus t. And if I have 1 over s plus 2, if I have 1 over s plus 2, this is e power minus 2t, and so on, from the table. Basically what I did is that I took this and put it in the exponent, I took this, I put it in the exponent, I took this and I put it in the exponent. And the question asks me for the coefficient k1, which is the coefficient of e power minus t, so I need a. How do I get a? I do the cover-up method, right? So I take this, 18s squared plus 66s plus 90, I cover up the denominator of a, so I cover up s plus 1, so I'm left with s plus 2 into s plus 3, and I evaluate everything by whatever makes the denominator of a equal to 0, so s equal minus 1. So I cover up the denominator of a in this expression in here, up. Sorry, that wasn't very clear. So in my expression in here, I cover up the denominator, so s plus 1 out, and I set the denominator of a equal to 0, so s plus 1 equal to 0, so s equal to minus 1. So here I covered up s plus 1, and I evaluate everything at s equal minus 1, whatever makes my denominator equal to 0. So a, which is equal to k1, equal to 18 minus 66 plus 90 over minus 1 plus 2 minus 1 plus 3. If I do my calculation, 18 minus 66 plus 90 over 2 over 1 times 2, this is equal to 21. If I go to my options, I find 21 is option D. Okay. In problem 13, consider f of s as given in equation 6 and its inverse Laplace f of t in equation 7. So this is equation 6. This is equation 7. Where a, b, and c are constants, find the value of f of t evaluated at t equal 1. So I need to do the entire Laplace transform of this f of s. So I can, because we have here we have really repeated roots, we can write this as a s plus 1 cube plus b s plus 1 square plus c s plus 1. Because we have really repeated roots, I put a constant divided by the denominator to decreasing powers. So 3, then 2, then 1. Okay? Now I need to find these coefficients a, b, and c. To find a, it's easy. A, we're gonna cover this up and evaluate it at whatever makes the denominator 0. So this is equal to 2.5 s squared evaluated at s equal to minus 1. So 2.5 into minus 1 squared, so 2.5. Easy. B is equal to, now b is 1 degree less than that of a. The denominator of b is 1 degree less than that of A. So I do a derivative d by ds of 2.5 s square evaluated at s equal minus 1. So I do the derivative, so 5s evaluated at s equal to minus 1, so this is equal to minus 5. C, I decrease the power one more time, so I do another derivative, so d square over ds square 2.5 s square evaluated at s equal to minus 1. But careful here, careful, is that if I do two derivatives, I need to multiply here by 2 factorial. Why? Because if, remember here, I had an s plus 1 cube, so both sides, here both sides, if I multiply everything by s plus 1 cube, I get, here side note, 2.5 s squared, this is equal to a plus s plus 1b plus s plus 2 square c, this is 1. Okay, now what I do here is that if I put s equal minus 1, this will cancel, I get a directly is 2.5. This is how the cover-up method works, and we need to explain this to explain why we got this 2 factorial in here. If I do the derivative, this will go out. The derivative of this is 1, I'm fine, I'm left with b. And the derivative of this will not die out, and I will have minus 1 plus 1, this will go to 0. So I have b equal to the derivative of this evaluated at s equal minus 1, which makes c equal to 0. This is b. C, I do the derivative 2 times. This go to 0 anyways. I derive this once, I get b. I derive this twice, b goes to 0. I derive this once, I get 2 s plus 1. I derive this again, I get 2 into 1 times c. So I get a 2, a factor of 2 in here. And this follows if I have s plus 1 cube d, I have 3 factorial d. This is how 2 factorial is multiplied by c. So if I do the derivative 2c, this is equal to, now I did the derivative once, the derivative once is 5s easily, we can see this, evaluated at s equal minus 1. This is equal to, derivative once again, this is 5 evaluated at s equal minus 1, so 5. So 2c is equal to 5, so c is equal to 2.5. So my f of t is equal to a over s plus 1 to the power of 3, but I know that this is a is 2.5, so 2.5 s plus 1 cube. Now if I will ignore the 1 because it's shifting, so I multiply by an exponential, so exponential minus t. Because I shift 1 unit, so I multiply by an exponential minus t. Now I have s cube. I remember that t of n goes to n factorial over s to the n plus 1. This is in the formula sheet. Now my denominator is s cube, so s plus 1, all of it cube. So n needs to be 2. N equal to 2. T square will go to 2 factorial over s cube. So the inverse Laplace of 1 over s cube is t square over 2. And I multiply by an exponential, so I shift here by plus 1. Right? So I already have the exponential, so I need t square over 2. This in here. This isn't included in the formula sheet. What's included in the formula sheet is this. This I only add a t, so this is plus b. b is 5. t, exponential minus t. And then finally 2.5, so plus 2.5 exponential minus t. This. All of this is multiplied by u at t. Okay? And finally I need to evaluate this at t equal 1. So f of 1, this is equal to, okay, let's see. I factor out e to the minus t outside, so I find 2.5 over t, 2.5 over 2, plus 5, plus 2.5, multiply all this by exponential minus 1, we get 3.21894. Yeah, okay, where did we go wrong? Yeah, okay. Here I have 5 as it's minus 5, so here I have minus, so not plus. So here I have minus, right? Because b is minus 5, I accidentally put it plus 5. So instead, I'm gonna put minus 5, and we get minus 0.4598 minus 0.5498. Done. Problem 14. I have f of s, and I need to find f at infinity. So basically, I need to find the limit t tends to infinity f of t. Unknown. Now, not included in the formula sheet. It's not included. I need to know the initial final value theorem, which is two parts, right? It tells you two things. First of all, it tells you that the limit t tends to 0 of f of t, this is exactly the same as limit s tends to infinity s f of s. 2, that the limit as t approaches infinity of f of t, this is equal to the limit s tends to 0 as f of s. Two things. Now here I need this limit, so instead let me compute this. So f of s is, if I multiply it by s, so s f of s, this will be s squared, this will be 14s, and this will be 625 normal. Okay? So yeah, so limit t tends to infinity f of t, this equals to as squared. Now we let s equal 0, right? So s tends to 0, so 0 plus 0 plus c over s squared, this is 0 plus 14s, this is 0 plus 625. Okay? Now they told me that the limit is 0.06, so 0.06 is equal to c over 625. So c is equal to 625 times 0.06. c is equal to 625 times 0.06, 37.5. Okay, this is everything really that you need for your exam. There's one more bonus. The level of this bonus is really it's high level. It will not come in the exam, but it's a fun little bonus. It's a fun little trick. So might as well give it to you because it's an interesting problem, right? So this is a bonus. We covered everything basically. This is everything that you need for chapter 7, chapter 8, and Laplace. If you can solve till here and get correct answers, then you're good, right? You're fine. You're gonna get 100, right? But I'm gonna solve this bonus. So here, the function f of x equals sine x over x shows up in many electrical engineering problems, so much so that it is called Sinc x function. And this function is the extension of f of x for f at 0 equal 1, because it's a popular limit, right? So x tends to 0, sine x over x is equal to 1. There's a geometric proof for it. I mean, you can also do L'Hopital, but it's not really a complete proof. Anyways, It's in our interest to compute the integral from minus infinity to plus infinity of this sinc function, which is the area under the entire curve. Use Laplace transform to do this. Now, yeah, it's correct. Sine x over x is an interesting, shows up in many electrical engineering problems, and the integral might be useful. So let's see the integral from minus infinity to plus infinity, sine x dx. Okay. Now, okay. Before I use Laplace transform, I know that the Laplace transform is defined from 0 to infinity f of t exponential minus st dt. So my time starts from 0. I don't start from infinity. So maybe I can create a 0 in here instead of minus infinity. Doing this is easy because sine x is odd. X by itself is odd. So sine x over x is an even function. So if it's even, so it's symmetric with respect to the y-axis. So I can do the integral on one side and multiply by 2. So this integral is twice the integral from 0 to infinity sine x over x dx. Now this resembles something, okay, which is if the Laplace transform, now I need to use the Laplace transform, right? Sine x over x is peculiarly similar to sine t over t, which is f of t to the t, which transforms into the integral from s to infinity f of u du. F of u is the Laplace of f of t, but instead of s I write a u just for completeness, for the notation of the integral. So if I find the Laplace of sine t and I divide it by t, I find this integral basically. So let's find the Laplace of sine t. Intuitively, this is 1 over s squared plus 1. This is easy to show. Now, this is Laplace of sine t. The Laplace of sine t over t, this is equal to the integral from 0 to infinity f of u, which is this, 1 over u squared plus 1 du. This is equal to arctangent, or tangent inverse, whatever you want to call it, of u, evaluated from infinity to s. So arctangent at infinity minus arctangent at s, which is equal to pi over 2. The limit of arctangent as x goes to infinity is pi over 2, minus arctangent of s. I'm gonna leave it arctan of s. Okay. Okay, so let's see. By definition, if I found the Laplace of sine t over t, I'll be finding 0 to infinity sine t over t exponential minus st dt, which is also equal to this, pi over 2 minus arctangent s. This equality holds. This is the definition of the Laplace transform. This is the definition. And this is whatever I got from here, from my analysis above. Let s equal to 0. Why? I get rid of this exponential. So I get the integral from 0 to infinity of sine t over t. Integral from 0 to infinity of sine t over t. Exponential 0 is 1, so I don't care about it. This is equal to pi over 2 minus arctangent of 0. Arctangent of 0 is 0. So there we go. Now I need twice that, so the integral from minus infinity to infinity of sine t over t dt. This is equal to twice the integral from 0 to infinity sine t over t dt. This is equal to 2 into pi over 2. This is equal to pi exactly. This was the bonus question. Of course, it's I'd say it's high level. It won't come in exams. You don't need to solve it, but it's an interesting problem. For those of you who are curious, we can find the integral of this using the Laplace transform and evaluate. Its evaluation is pi. Okay, so that's it for the revision session. Hope you found it clear, hope you find it beneficial for you, and trust me very well, if you can solve this, you can easily get 100 in the exam and have plenty of time left on the clock during the exam. So good luck with your quiz 1, and I'll see you in revision session 2 hopefully. Good luck.